Okay, thanks a lot. So thanks a lot for the kind introduction and for inviting me to give this talk. As mentioned, title of my talk is the tropical geometry of monotone Hurwitz numbers. And so this talk is partially based on joint work with Jan Willem van Ittersum, Felix Leit, Reinier Kramer, and Danilo Lewanski, and then also a single joint work Lewanski. So before I start with the actual contents, I want to begin with an introduction and give some very general context. So today's talk is on Hurwitz numbers, as the title says, and Hurwitz numbers are important enumerative invariants in algebraic geometry. They enumerate holomorphic maps between Riemann surfaces, and here we have such an example. So here I have a genus 2 Riemann surface and a genus 1 Riemann surface, and I simply look at a holomorphic map from this surface to this surface. And of course, these maps have to satisfy certain properties. Now, Hurwitz numbers were originally introduced by Adolf Hurwitz himself in the 1890s, and the original motivation was to solve the, at the time, open problem of proving the irreducibility of the modular space of genus G curves. Later on, this was proved with other methods, but this was nevertheless the original motivation to study these numbers. Now, after Hurwitz's work in the 1890s, and then he also published a paper, if I remember correctly, in 1901. So after that, the field of Hurwitz numbers, so the study of Hurwitz numbers lay dormant for the majority of the 20th century. But this has radically changed since the 1990s. So since the 1990s, we have seen rapid developments in their study due to, at the time, newfound deep connections with Gromov-Witten theory and string theory. So one of the amazing things about Hurwitz numbers that we saw in the last 30 years is that Hurwitz numbers show up in all kinds of mathematical fields. So originally they come from algebraic geometry and complex analysis and also algebraic topology in some sense. But they also show up in the representation theory of the symmetric group, in Gromov-Witten theory, in combinatorics, in mathematical physics, and operator theory. And in some sense, we will see all of these fields in today's talk. So today's talk focuses on a very specific class of Hurwitz numbers, which are so-called monotone Hurwitz numbers that originate in random matrix theory. Today's talk is in some sense a progress report of a program towards connecting monotone Hurwitz numbers to Gromov-Witten theory via the combinatorial methods of tropical geometry. So I summarized this goal of the program in this figure here. So I have Hurwitz theory, the theory of Hurwitz numbers, Gromov-Witten theory, and a random matrix theory. And the goal is to use something that is called tropical geometry, which provides combinatorial methods to study problems in algebraic geometry to connect all these three fields with each other. And this is a larger program. Lots of people are working on this. And so, on the general connection between Hurwitz theory, random matrix theory, and Gromov-Witten theory, and my contribution in this is using these combinatorial methods from tropical geometry. And what this gives, we will see later on in the talk. Okay, so the plan for today's talk is to first give an introduction to Hurwitz theory. Very gentle, very short, and then in the second part I will discuss connections to Gromov-Witten theory and very briefly explain what it is. The third part, I will then talk about monotone Hurwitz numbers and how they show up in random matrix theory. In the fourth part, I will discuss so-called tropical monotone Hurwitz numbers, so a combinatorial approach to study these numbers. In the fifth part, we will discuss connections from monotone Hurwitz numbers to Gromov-Witten theory via something which is called an ELSV type formula. And in the last part, if I have time, I want to take a very short excursion to mirror symmetry to also mention what these connections between Hurwitz numbers and mirror symmetry is, or at least give an application of mirror symmetry to Hurwitz theory. Okay, so let's start with an introduction to Hurwitz theory. I just want to very quickly recall what a Riemann surface is. So a Riemann surface is a one-dimensional complex manifold. And Hurwitz theory is concerned with the enumeration of holomorphic maps between compact Riemann surfaces, which corresponds to finite regular morphisms between complex algebraic curves, complex smooth algebraic curves. Okay, so let's take such a holomorphic map between compact Riemann surfaces. So let S1 and S2 be compact Riemann surfaces, and F from S2 to S1 be a non-constant holomorphic map. So the constant maps are, of course, boring. So we look at the non-constant maps. And then one of the first observations, so one of the very nice properties of these maps is that they have a very interesting local structure. Namely, for all y in S2, so we take a point in the source curve. So in this S2 right here, we have that f locally at y is given by z is mapped to z to the ny, which means that locally at every point, this map f is given as a monomial map, and this ny is a positive natural number. All right, so let's look at this in the picture. So once again, we have this picture from before. We have a holomorphic map between two compact Riemann surfaces. We take the point y and we take the point f of y, and we can look at open charts around y and f of y, and in the coordinates of these local charts, this map is given by z is mapped to the z to the ny, where ny is a positive natural number. So once you actually have this monomial structure, this ny doesn't depend on the choice of the charts. So of course you have to choose the charts in such a way that you actually get a monomial map. But once you chose charts in such a way that you have a monomial map in the local coordinates, this ny is invariant. So this ny is an invariant of the map at the point y. First observation is, first of all, we call this ny the ramification index of y. So this is the name of this ny, and this is going to be a very important notion in the theory of Hurwitz numbers. Well, the first observation is that for all but finitely many y, we have that the ramification index is equal to 1. So in other words, so if I take such a non-constant holomorphic map between two compact Riemann surfaces, this map at almost all points, except for finitely many exceptions, is locally a linear map. So this is what the local structure is, and I might have finitely many exceptions where the map is more complicated. Okay, so let's introduce some more notation. So once again, we look at a holomorphic map, non-constant between two compact Riemann surfaces, and now we take a point in the image curve. So we take a point x in S1. And then the first observation here is that the pre-image of x is always a finite set. So this is always true. And then associated to x, then we associate to x a tuple of positive natural numbers, namely the tuple mu x, which consists of the ramification indices in the pre-image of this point x. And so this tuple of ramification indices in the pre-image is called the ramification profile of x. So once again, let's look at this picture. So here I have a point x. I look at the pre-image. In this case, the pre-image, so in this image, has 5 points, so y1 to y5. And then the ramification profile of x is exactly the tuple consisting of the ramification indices at the points y1 to y5. So this is what the ramification profile of x is. The first fact is here that all ramification profiles mu x are indeed partitions of the same number d. So if I sum over the entries of any ramification profile of x, so if I take any x, I look at the ramification profile, and I sum over the entries, I always get the same positive natural number, that is d. And this d we call the degree of f, and we denote it by deg of f. Okay, so now there are some ramification profiles that show up more often than others in Hurwitz theory, and I want to give names for 2 of them. So recall that for all but finitely many points in S2, the ramification index was equal to 1. Therefore, for all but finitely many points x in S1, we have that the ramification profile is the trivial partition of D. And this in particular means that x has exactly degree of f many pre-images. And we call such points x in S1 unramified. Now, the easiest non-unramified case is a so-called simply unramified case, which is the following. So if the ramification profile is 2, and then only once we call x simply ramified. That means I have one point in the pre-image of x that has ramification index 2, and at all the other points the map is locally linear in the pre-image of x. All right, so now what are Hurwitz numbers? So let S1 be a compact Riemann surface. Then Hurwitz numbers count holomorphic maps f from S2 to S1 with prescribed ramification data. So what this means, for every point in S1, I fix the ramification profile. So I count all holomorphic maps from a compact Riemann surface S2 to the given compact Riemann surface S1, such that every point x in S1 has a prescribed ramification profile. So let's look at this in a picture. So I have a map from S2 to S1. In this case, I have a degree 6 map. And for every point on S1, which here is illustrated by a line, but in general, so of course, this is just a schematic picture. So for every point on S1, I fix the ramification profile. So here I have this point, for example, where I fix that the map has to have ramification profile 3, 2, 1. And indeed, so in this picture, I have one point which has local degree 3, local degree 2, and local degree 1. The same for 2, 2, 2. And we see that all of those, so 3, 2, 1 and 2, 2, 2 are indeed partitions of 6. Now here for this point, for example, I fix that it has to be unramified. So I have 6 pre-images because I have a degree 6 map. And I have one point that might be, so I have one point where I fix that it has to be simply ramified. So I have one point in the pre-image of degree 2 and 4 points in the pre-image of degree 4. All right, so this is what Hurwitz numbers are. Hurwitz numbers simply count non-constant holomorphic maps from S2 to S1, where S1 is given, and we fix the ramification profile of every point in S1. So of course, I can be very wild in prescribing this ramification data, but some specifications of ramification data yield Hurwitz numbers of particular interest. That means if I choose this ramification data in a certain way, in a certain interesting way, I actually get some nice structures. And one of the most studied cases are so-called double Hurwitz numbers, which have a very specific way to prescribe the ramification data. And I simply want to define those. So let d be a positive integer, so d is strictly bigger than 0. So of course this d is going to be the degree of a non-constant holomorphic map. I fix r bigger or equal than 0, so this is a non-negative natural number, and I fix 2 partitions of d, mu and nu. And of course mu and nu are going to be ramification profiles. Furthermore, let P1 be the Riemann sphere. So this is the Riemann surface S1 and on the previous file. So this is the target of these non-constant holomorphic maps. And we further fix r points on P1. So this is what this r is for. So I fix r many points on P1 that I denote by P1 to PR. So then double Hurwitz numbers H, R, mu, nu count holomorphic maps from F from S to P1, such that S is a compact Riemann surface. The ramification profile of the south pole of the Riemann sphere is mu. The ramification profile of the north pole of the Riemann sphere is nu. The ramification profile of these points P1 to PR is simply is 2 and only 1. So these PI are simply ramified. And all the other points on the Riemann sphere are supposed to be unramified. So this is what double Hurwitz numbers are. Let's once again look at this in the picture. So here I have the south pole, so this is 0. I have the north pole, and this is infinity, and I prescribe that the ramification profile of 0 is supposed to be mu. The ramification profile of infinity is supposed to be nu. Here I fixed r is equal to 3, so I have 3 extra points on the Riemann sphere where I fix that the ramification profile is simple. So I have the ramification profile 2 and only once over these points P1 to P3, and all the other points on the Riemann sphere are simply ramified. So this is what the condition is. Then I simply count all possible non-constant holomorphic maps from any compact Riemann surface to this Riemann sphere. So this is what the definition of double Hurwitz numbers are. And of course they are called double Hurwitz numbers because I have 2 points where I can have arbitrary ramification, namely 0 and infinity. Okay, so the first question you might ask is, if I count these maps, why is this always a finite number? So I claim that these are numbers, but of course it could be that there are simply infinitely many maps. And so this is a question actually Adolf Hurwitz addressed in his original work in the 1890s. Namely, what Hurwitz observed is the following. So in his original paper, Hurwitz proved Hurwitz numbers may be computed via factorizations in the symmetric group. So he proved that if I take such a map, I get a certain factorization in the symmetric group, and vice versa. And this actually proved that this is always a finite number. I want to show how this works for double Hurwitz numbers. In order to show this, I briefly have to introduce some notation. So let sigma be a permutation in S. We call these so-called associated partition its cycle type C of sigma. So if you don't know what the cycle type C of sigma is, it is simply the partition that corresponds to the conjugacy class of sigma. If you also don't know what that is, I will simply show you in an example, and you will immediately understand what the cycle type is. So I have a permutation here, 1, 2, 3, 4, 5, and 6. And the cycle type of this is simply 3, 2, 1, because I have one cycle of length 3, I have one cycle of length 2, and I have one cycle of length 1. So if I have a permutation sigma, I simply decompose it into disjoint cycles, and I record the length of the cycles in this decomposition. And the tuple of the length of these cycles is exactly the cycle type. So this is always a partition of D. So in this case, we live in S6, and this is a partition of 6. All right, so this is what the cycle type is, and this is the key to compute Hurwitz numbers via factorizations in the symmetric group. All right, so Hurwitz proved in 1892 the following statement. So let D once again be a positive integer, R a non-negative integer, and two partitions of D, mu and nu. So it's the same data as in the definition of double Hurwitz numbers. Then we have that the double Hurwitz number is equal to 1 over D factorial times the cardinality of a set. And the set is a set of tuples of permutations. So it's tuple sigma 1, tau 1 to tau r sigma 2, where sigma 1, sigma 2, and the tau I, so all these tau I live in the symmetric group SD. The cycle type of sigma 1 is equal to mu. So the cycle type of sigma 1 is simply the ramification profile of the south pole of the Riemann sphere, so 0. The cycle type of sigma 2 is equal to nu. So the cycle type of sigma 2 is the ramification profile of the north pole infinity of the Riemann sphere. Okay, so these tau I are transpositions. So what is the cycle type of a transposition? It is simply 2 and then only once, right? So I have 1, 2 cycle, and then I have only one cycle if I actually completely decompose it. And therefore, the cycle type of this transposition is exactly the cycle type of the points P1 to PR that are fixed on the Riemann sphere in the definition of double Hurwitz numbers. And then I even have one more condition, namely that the product sigma 1, tau 1 to tau r is exactly equal to sigma 2. So this is the last condition, and therefore double Hurwitz numbers may be computed in terms of factorizations in the symmetric group with prescribed cycle types. So this is what Hurwitz proved in 1892, and this is of course a very amazing theorem because we started with this very complicated algebraic geometry problem where we wanted to count non-constant holomorphic maps between Riemann surfaces, and Hurwitz told us we can simply do this in terms of factorizations in the symmetric group. All right, so let's use this maybe to show how to compute a double Hurwitz number. So we fix the following data. So let D be equal to 4, R is equal to 3. We take a partition mu of 4, a partition nu which is equal to 2, 2, which is also a partition of 4. And this is the discrete data that we fix. Okay, so let's look at one possible tuple, sigma 1, tau 1 to tau 3, because we have R equal to 3, and then also sigma 2. So let's look at sigma 1 is equal to 1, 2, 3, 4. Tau 1 is equal to 1, 4. Tau 2 is equal to 2, 3. Tau 3 is equal to 1, 3. And sigma 2 is equal to 1, 3, 2, 4. So first thing that we check is the cycle types. So the cycle type of sigma 1 is 4, because I have 1, 4 cycle. This is exactly the cycle type mu. So that's fine. I indeed have tau 1 to tau 3 are transpositions. Their cycle types are indeed 2, 1, 1. So this is exactly what we prescribed in what Hurwitz prescribed in his theorem. And then we also have that sigma 2 is equal to 1, 3, 2, 4, and the cycle type of sigma 2 is simply 2, 2. So the cycle types fit, and now if you actually look at this product, you indeed see that sigma 1, tau 1 to tau 3 is equal to sigma 2. So this tuple is fine. And then simply what you do is you proceed through all possible tuples, and in the end, in this case, you obtain that the double Hurwitz number is equal to 14. So this theorem of Hurwitz actually reduces the study of Hurwitz numbers, and this is actually true for all possible Hurwitz numbers, not just for double Hurwitz numbers, but it's very easy to state for double Hurwitz numbers. So Hurwitz theorem reduces this problem of computing Hurwitz numbers to counting factorizations in the symmetric group. All right, so this is the end of my introduction to Hurwitz theory, and now I want to discuss connections to Gromov-Witten theory. First of all, I quickly want to say what Gromov-Witten theory is, even though I'm not going to go into detail, but at least I'm going to give some motivation. So Gromov-Witten theory originated in mathematical physics by work of Gromov and Witten, as the name says. And so this is quite old, so it's the late 1980s and early 1990s, I would say. So this is really the start. And shortly after the inception of Gromov-Witten theory, these connections to Hurwitz numbers played a very significant role. Okay, so now Gromov-Witten theory studies the intersection theory of parameter spaces of curves, more precisely the moduli spaces of curves. And the central objects in this study, so in this theory, in the Gromov-Witten theory, are so-called Gromov-Witten invariants, which are exactly the intersection products. So you simply intersect certain subspaces of these moduli spaces, and then if you get a zero-dimensional thing, this is exactly your Gromov-Witten invariant. So this is what Gromov-Witten invariants are, and this study of Gromov-Witten invariants revolutionized enumerative algebraic geometry ever since its inception, and it led to very many amazing results in enumerative algebraic geometry. So the main idea is, in order to enumerate all curves satisfying conditions that we call A1 to AN, one observes that each AI corresponds to a subvariety in the respective moduli space. So the subvariety is simply all the curves that satisfy this condition AI. And then the total number of curves which satisfy all these conditions is exactly the degree of the intersection product of the corresponding subvarieties of the moduli spaces. So this is roughly the idea of Gromov-Witten theory. So of course, this is a very complicated study in principle, but this is the main idea that is employed to enumerate, to study enumerative algebraic geometry problems via these Gromov-Witten invariants. Okay. So the connections between Gromov-Witten theory and Hurwitz theory are especially via something which we call the ELSV formula, which is a very celebrated result from 1991 or 2001, depending on what you count. So in 1999, not 1991. So 1999 and 2001. So in 1999, Eckeder, Lando, Shapiro, and Weinstein announced a very specific formula for a certain subclass of double Hurwitz numbers, and the proof was then given in 2001. And the result is the following. So let D be a positive integer once again, R be a non-negative integer, and we take two partitions of D, where the second partition in this case is trivial. So we fix that the ramification profile of infinity is simply trivial. So in other words, infinity is unramified in the double Hurwitz number. And then Eckeder, Lando, Shapiro, and Weinstein proved that we have the double Hurwitz numbers for this case, where this nu is trivial, are equal to a certain combinatorial factor, which only depends on mu, times the Gromov-Witten, times certain Gromov-Witten invariants of the moduli space of genus G curves with n-mark points. So this is of course one of the most studied moduli spaces in algebraic geometry. And essentially what this theorem says is Hurwitz numbers enumerate, or in other words, compute certain Gromov-Witten invariants. So enumerate here is wrong. So Hurwitz numbers compute certain Gromov-Witten invariants. And this was a very big statement at the time, because at the time one actually didn't know how to actually compute these Gromov-Witten invariants. And what Eckeder, Lando, Shapiro, and Weinstein essentially proved is that these very complicated objects, these Gromov-Witten invariants, may be computed in terms of factorizations in the symmetric group. And this is one of the most powerful results in modern enumerative algebraic geometry. So the ELSV formula has many important applications. So for example, the ELSV formula implies various important theorems on the intersection theory of the moduli space of genus G curves with n-mark points. So for example, Witten's conjecture or Konsevich's theorem, the Virasoro constraints, or Faber's lambda G conjecture. So all of these theorems were already known, but they follow very, very briefly from the ELSV formula. So the ELSV formula is a very powerful result, which implies all these theorems, which mathematicians worked very hard for a very long time to prove, and the ELSV formula very briefly proves them. Paper by Kazarian from, I think, 2007 or 2008, where on 40 pages he proves all of these results as a direct consequence of the ELSV formula. So it's a very powerful theorem. But the ELSV formula also has applications to Hurwitz theory. So for example, it implies the Goulden-Jackson conjecture from 1999 in one line. So once again, what does this say? So we take a positive integer D, a non-negative integer R, and two partitions of D, where the partition nu is trivial, as in the statement of the ELSV formula. And then we have the double Hurwitz numbers are equal to a combinatorial factor times a polynomial in mu. So PG of mu is a polynomial in the entries of the partition mu. So this is what Goulden and Jackson in 1999 conjectured, and it indeed follows from the ELSV formula in one line. And it took Hurwitz theorists, I think, 17 years to come up with a proof of this conjecture, which actually doesn't rely on the ELSV formula, and it used some very deep representation theoretic theorems to actually answer, so to actually prove this conjecture independently from the ELSV formula. So this is actually a very deep structural result on the structure of double Hurwitz numbers, where we have that the partition mu is trivial. Okay, so this entire discussion that I just lined out always relied on the fact that mu is trivial. So it is a sort of natural question to ask, what about other nu? So what if the point infinity, what if the North Pole isn't unramified in the double Hurwitz number, and I simply want to consider other nu? And this is one of the main programs in Hurwitz theory, and in some sense it was initiated in 2005 by Goulden, Jackson, and Vakil, because in 2005 Goulden, Jackson, and Vakil proposed a program towards an ELSV type formula for all double Hurwitz numbers, so for all kinds of choices of nu. So this is what Goulden, Jackson, and Vakil wanted to study in 2005, and the idea of this program was the following. Because this Goulden-Jackson conjecture is such a deep structural theorem on the structure of double Hurwitz numbers when nu is trivial, the idea is to first now derive the polynomial behavior of double Hurwitz numbers for any nu, and then from this polynomial behavior reconstruct an ELSV type formula. So this is what Goulden, Jackson, and Vakil proposed in 2005, and they already made first steps towards this direction. So in order to state their theorem, I first have to introduce this set here, HMN. So we have two positive integers, m and n, and they are positive natural numbers. And we consider this set HMN, which is the set of all tuples mu and nu, and n to the m cross n to the n, such that the sum over the entries of mu is equal to the sum over the entries of nu. So in other words, this is the parameter space of all tuples of partitions of a fixed length and of the same size. So this is what this space is. So I simply look at partitions mu of length m and partitions nu of length n, and they are supposed to be partitions of the very same positive natural number. Okay, so this is the set, and then Goulden, Jackson, and Vakil proved the following theorem. So let R be a non-negative integer, and then we consider the map HMN to the rational numbers, where we map mu and nu to the double Hurwitz number HR mu and nu. And then Goulden, Jackson, and Vakil prove that this map is indeed piecewise polynomial. So what does this mean? That this is a piecewise polynomial map. What they proved is that there is indeed a hyperplane arrangement in this set HMN. So if you look at this, at the structure of the set HMN, this is nothing else than a hyperplane in n to the m cross n to the n, because I live in a linear subspace essentially, right? Because I cut out the set in n to the m cross n to the n by a linear equation. And then what they say is that what they proved is that there is a hyperplane arrangement in HMN, such that this map, which takes mu and nu to the double Hurwitz number, is polynomial in each maximal cell of the complement. So let's look at this hyperplane arrangement right here. So I have the cells C1, C2, C3, C4, C5, C6, for example. And in each cell, there exists a polynomial PCI, such that this polynomial PCI computes this double Hurwitz number for all choices of partitions in this cell. So this is what Goulden, Jackson, and Vakil proved. And this led them to the following conjecture, which was later generalized by Gebayer, Cavalieri, Johnson, and Markvich in 2012. And the conjecture is a very concrete proposal for an ELSV type formula for double Hurwitz numbers. Okay, so now you want to prove this conjecture. This is the ultimate goal. this conjecture. In order to do this, the first idea is, of course, to understand this polynomial structure better. So we know now that there exists a polynomial structure, but we first have to understand it better to actually prove this conjecture. And first steps in this direction were made by Shadrin, Shapiro, and Weinstein in 2006, where they asked the question, what is actually the difference between the polynomials in different cells? So if I look at these pictures, so I have a polynomial here and I have a polynomial there. So what is the difference between them? Could they be equal, or is there some interesting structure which relates this polynomial here to this polynomial there? So this is what Shadrin, Shapiro, and Weinstein asked. And they sort of solved this in the case of genus 0, but the complete answer was given in 2010, where Cavalieri, Johnson, and Markvich proved that the difference of two polynomials PC1 minus PC2 may be expressed recursively in terms of Hurwitz numbers with smaller input data. So when I cross this wall from one cell to another cell, the difference of the polynomials computing double Hurwitz numbers can be computed in terms of Hurwitz numbers with smaller input data. So with smaller r and with partitions mu and nu of smaller size. So of smaller length is what I meant. So of smaller length. So this is what Cavalieri, Johnson, and Markvich proved. So and in this way, in some sense, these polynomials may be computed recursively. And this is what we call a recursive wall-crossing formula. And this is essentially where we're at with regards to the Goulden, Jackson, Vakil, and Bayer, Cavalieri, Johnson, Markvich conjecture. So since 2010, there has been strong progress, but the Goulden, Jackson, Vakil, and Bayer, Cavalieri, Johnson, Markvich conjecture remains open. Yeah. Okay. So this is the story for classical Hurwitz numbers.
Sorry, is it easy to say what these walls like are? Is there some nice description of them, or not really?
No, you can actually write it down. So okay, so the sum here is the sum over all entries of mu and all entries of nu, right? And the walls are essentially taking subsets. So you take all subsets of the set 1 to the m and all subsets of the set 1 to the n. So let's say I is a subset of 1 to the m and j is a subset of 1 to the n, and then you simply look at the sum over the mu I where I lives in I, and the sum over nu j where j lives in j, and this is exactly what cuts out these linear subspaces.
So when those two subsets sum to give you the same.
Exactly. Yeah.
Okay. Thank you.
So this is what these walls are. Apparently called the resonance arrangement, which is a very much studied hyperplane arrangement by combinatorials, but this is something that I don't know much about. But apparently this is a hyperplane arrangement which is of interest in combinatorics.
And so the smaller input data in this theorem has to do with these i's and j's that you were talking about, I guess. Is that okay? Great.
Exactly. Yeah. Thanks. This is what the small input data is essentially. So you simply take subsets, and then so you have a partition of length I and a partition of length I and a partition of length j. And so this allows you to compute the difference between these polynomials, computing the double Hurwitz number.
Thanks.
Yeah. Okay, you're welcome. Okay, so this is the story for the classical Hurwitz numbers, and I would like to come to the monotone Hurwitz numbers, which originate from random matrix theory. Yeah. Okay, so the starting point of this study is the so-called Harish-Chandra-Itzikson-Zubair integral, which is a central object in random matrix theory, and it looks like this. And I don't want to say what it is, but it is a object in a random matrix theory, which apparently has very many applications. But the story of monotone Hurwitz numbers starts with the theorem of Goulden, Guy, Paquet, and Novak in 2011, where they proved the following. The coefficients in the Taylor expansion of the HCIZ integral are so-called monotone double Hurwitz numbers. So if you look at the Taylor expansion of this this strange object from an algebraic geometrist point of view, you simply look at the Taylor expansion. The coefficients in this Taylor expansion may be expressed in terms of something which looks like a double Hurwitz number, essentially. The original motivation for this theorem was to prove a conjecture about the convergence of this integral here, which was ultimately proved with using these monotone double Hurwitz numbers in 2020 by Novak. But since this theorem in 2011, the study of monotone double Hurwitz numbers has taken a life of its own, and this is essentially where also my research starts. So my research starts in some sense with this theorem right here. Okay, so to explain this, I first want to tell you what monotone double Hurwitz numbers are. So Goulden, Vakil, and Novak in 2011 actually came up with the definition of monotone double Hurwitz numbers, and you will see in a second why they are called monotone double Hurwitz numbers. So first of all, you fix the same data as before. You have a positive natural number d, you have a non-negative integer r, and you have two partitions of d, mu, and nu. And then we define monotone double Hurwitz numbers in the setting of the symmetric group. So we have this monotone double Hurwitz number right here, h, r, mu, nu, where in this case we put an arrow over this to indicate that this is a monotone double Hurwitz number, and we define this as equal to 1 over d factorial times the cardinality of a set, and this is a set of tuples sigma 1, tau 1 to tau r sigma 2, where the first first four conditions are exactly the four conditions provided by Hurwitz's theorem. So we have permutation sigma 1, sigma 2, tau I in the symmetric group SD. The cycle type of sigma 1 is equal to mu. The cycle type of sigma 2 is equal to nu. These tau I are transpositions. We have that sigma 1, tau 1 to tau r is equal to sigma 2. So these are exactly the four conditions that are outlined earlier. But now I have indeed one more condition, namely that tau I is equal to RISI. So because tau I is a transposition. And I fix that Ri is smaller than Si. I can always choose this in such a way. And then I force that the factorization that I look at satisfies that Si is smaller or equal than Si plus 1. So this is where the monotone comes from, because I force essentially this factorization that if I look at the bigger element in the transpositions as I proceed through this product, doesn't decrease. So it can only increase or stay the same, and this is where the monotone double Hurwitz number comes from. So this is what the definition is. And so let's compute one monotone double Hurwitz number using this symmetric group setting, and we have the same data as before. So we fix d equal to 4, r equal to 3, the partition mu is equal to 4, and the partition nu is equal to 2, 2. Okay, so first of all, we look at the factorization that we looked at earlier. So sigma 1 equal to 1, 2, 3, 4. Tau 1 is equal to 1, 4. Tau 2 is equal to 2, 3. And tau 3 is equal to 1, 3. And sigma 2 is equal to 1, 3, 2, 4. We've checked earlier that this indeed fixes, that this indeed satisfies the cycle types. And we also checked that this is indeed the right product. But if we want to look at the monotonicity condition, we see that this fails here because 4 is bigger than 3, right? So here I have, so R1 in this case is 1, and S1 is equal to 4. And R1 is equal to 2, and S2 is equal to 3, but S1 is bigger, strictly bigger than S2, and therefore the monotonicity condition fails here. And therefore this tuple does not count to the monotone double Hurwitz numbers associated to this data. Okay, so let's look at one more factorization. So here I have sigma 1 equal to 1, 2, 3, 4. Tau 1 is equal to 1, 2. Tau 2 is equal to 1, 3. And tau 3 is equal to 2, 3. And sigma 2 is equal to 1, 4, 2, 3. So these are the same cycle types as before. And indeed, we also have that this product formula holds. Now, if we want to check whether the monotonicity condition holds, we simply have to check that 2 is smaller or equal than 3 is smaller or equal than 3. And this is indeed true. And therefore, this factorization counts for the monotone double Hurwitz number. And proceeding tuples, we obtain that the monotone double Hurwitz number is a rational number that is given by 25/4. Okay, so these monotone double Hurwitz numbers, they are always smaller or equal to the classical double Hurwitz numbers, and this is exactly what the condition here is. So and here we get 25/4. All right, great. So now the question is, we had this connection between classical Hurwitz numbers and Gromov-Witten theory, and the question now is there also a connection between monotone Hurwitz numbers and Gromov-Witten theory? And this is one of the most studied questions since 2011 in Hurwitz theory as well. And this is a question that I also worked on and still work on, and our ansatz that we choose is via tropical geometry. And our long-term goal is to derive an ELSV type formula for monotone double Hurwitz number. So this is the long-term goal of this research project, but this is still a very much open problem. So for classical double Hurwitz numbers, we have been quite close with regards to this Goulden, Jackson, Vakil conjecture, but for monotone double Hurwitz numbers, this is still a long way to go. All right, but this is anyways the long-term goal. Now I want to come to tropical monotone Hurwitz numbers and also say what tropical geometry is. So tropical geometry is a conceptualization of a combinatorial approach to algebraic geometry. It started in the early 2000s through work of Grisha Mikhalkin and Bernd Stumpfels, and especially Mikhalkin followed a suggestion of Maxim Kontsevich. So the idea is that you use something which is called a tropicalization, which is a transformation of algebra geometric objects to combinatorial objects. And this is, for example, what this looks like for Riemann surfaces. So if you start with a Riemann surface, this tropicalizes to a combinatorial graph. Now, if you look at Hurwitz numbers, they enumerate holomorphic maps between Riemann surfaces, and therefore it is natural to assume, using this tropical geometry approach, that there also exists a graph theoretic interpretation of of classical double Hurwitz numbers. And this is indeed true. So Cavalieri, Johnson, and Markvich in 2008 applied this tropicalization technique to obtain a graph theoretic interpretation of classical double Hurwitz numbers. And this tropical interpretation of classical double Hurwitz numbers played the central role in their proof of the recursive wall-crossing formula in 2010. So now what we want to do is we also want to obtain a tropical interpretation or a graph theoretic interpretation for monotone double Hurwitz numbers. But one of the problems is that monotone double Hurwitz numbers are only defined in the setting of the symmetric group and do not have a geometric interpretation. That essentially is essentially this comes from the fact that monotone factorizations are not preserved under conjugation. So this is essentially the reason why monotone double Hurwitz numbers do not have a geometric interpretation, because this fact that in the classical case, so in Hurwitz's theorem, the factorization that you look at are preserved under conjugation is a central fact, so is a central step in proving this theorem. And here this is not true, and therefore we cannot move to the world of Riemann surfaces, but we simply have to work in the setting of the symmetric group. So we sort of have to do something else, and the idea that we had was to use the fermionic and the bosonic Fock space. So the fermionic Fock space is a representation theoretic tool that comes from the Kyoto group in the theory of integrable systems. And essentially, the idea of this approach that we use is the following. So we start with this monotone Hurwitz numbers, and we want to establish a connection between monotone Hurwitz numbers and tropical geometry. And the first thing that other people did, namely Alexandrov, Lewanski, and Chadrin in 2016, was to prove that monotone Hurwitz numbers may be expressed in terms of this representation theoretic space, which is called the fermionic Fock space. Now there's something known, which is called the boson-fermion correspondence, which essentially tells you that the fermionic Fock space and the bosonic Fock space are sort of the same thing. So if you have an object in the fermionic Fock space, you can always express it in the bosonic Fock space and the other way around. So this is what the boson-fermion correspondence tells you. So this comes from some physics words, but it is a very precise mathematical statement. And then the very last step is something that is known in the tropical geometry literature, namely that if you have an expression in the bosonic Fock space, so in this representation theoretic space right here, you can always transfer this into the graph theoretic language of tropical geometry, and the slogan here is sort of the tropicalization is equal to the bosonification. So this is essentially the route that we take. So instead of going from monotone Hurwitz numbers to tropical geometry directly, we first moved through this representation theoretic machinery, and then ultimately obtained an interpretation in tropical geometry. And this is simply something that we wanted to work out to also obtain a study of the polynomial structure of monotone double Hurwitz numbers. But in fact, working this out also led to a very surprising theorem that I want to show you on the next slide. So a single-authored work in 2017, but in this form, in the joint work with Lewanski in 2018, we proved the following statement, namely, let D be a positive natural number, R a non-negative natural number, and U be partitions of D. So the same data as always for double Hurwitz numbers. And then we have that the monotone double Hurwitz number is a sum over finitely many oriented graphs. Oh, sorry, there's a German word. So this means where. So where the monotone double Hurwitz number is a sum over finitely many oriented graphs, and each such graph is weighted by something which is called a relative Gromov-Witten invariant. So what we show by passing through this fermionic Fock space, bosonic Fock space to the graph language, what we showed is that relative Gromov-Witten invariants indeed compute monotone double Hurwitz numbers, and that is something that surprised us when we showed this, and this was the first connection between monotone double Hurwitz numbers and Gromov-Witten theory. Okay, so but in some sense this is the other way around. So what we actually want is that these monotone double Hurwitz numbers compute Gromov-Witten invariants, and so this is what this next section is going to be about. So towards an ELSV type formula for monotone Hurwitz numbers. So I want to say an ELSV type formula for monotone double Hurwitz numbers is an open problem. The idea to derive this formula is to follow the approach of Goulden, Jackson, and Vakil via the polynomial structure of possible polynomial structure of monotone double Hurwitz numbers that we haven't seen yet, but indeed monotone double Hurwitz numbers also satisfy a polynomial structure. So this is the idea, and in 2014, Goulden, Pakir, and Novak, the people that first come up with the notion of a monotone double Hurwitz numbers, proved the following monotone analog of the Goulden-Jackson-Vakil theorem. Namely, monotone double Hurwitz numbers are piecewise polynomial with the same hyperplane arrangement as their classical counterparts. So if you look at this function that takes a tuple mu to the corresponding monotone double Hurwitz numbers, you can simply look at the same walls in this space HMN. And indeed, in each chamber there, we will see that monotone double Hurwitz numbers are polynomial for choices of partitions in these chambers. So this is what Goulden, Pakir, and Novak proved, and this is a very so this means that monotone double Hurwitz numbers very much satisfy a very similar behavior as their classical counterpart. So one of the problems with this theorem, of course, this is a great theorem, but this theorem is purely in existence theorem, whereas the Goulden-Jackson-Vakil theorem actually showed us how to compute these polynomials that are involved in computing the double Hurwitz numbers. So if you actually want to test some conjectures, this theorem doesn't tell you how to come up with examples of these polynomials. So that is one of the theorem. So that is one of the problems with this theorem. The other problem is that the wall crossing formula, at least to my knowledge, are not approachable with the involved methods, and Goulden, Pakir, and Novak stated this as an open problem in their paper. So these are the two problems with the theorem that we wanted to solve in our work. So first of all, using the tropical geometry interpretation for monotone double Hurwitz numbers via these relative Gromov-Witten invariants that I showed earlier, we proved the following theorem in the series of work. So one single authored, one paper with Reinier, Kramer, and Danilo, Lewanski, and then lastly in 2019 a paper with Danilo, Lewanski, where we proved the following. So first of all, we derived algorithms to compute monotone double Hurwitz numbers. And then using this structure, we also showed that monotone double Hurwitz numbers admit recursive wall-crossing formulae. So how do we prove this? Well, first of all, we use this tropical interpretation of monotone double Hurwitz numbers as a finite sum of oriented graphs weighted by relative Gromov-Witten invariants. And then we observed that these relative Gromov-Witten invariants, so this weight is a discrete is in some sense a discrete integral over a polytope. And therefore we obtained this polynomiality statement via Erhard theory. Moreover, using this Erhard theory statement, what we did was we proceeded with a combinatorial analysis of the structure of the polytopes in the different maximal cells of the hyperplane arrangement. And so if you look at the polytopes, for example, in this chamber and the polytopes that show up in this other chamber, you can sort of see that if you move this polytope through this wall, that the polytope sort of changes shape. So that is sort of what happens. And this changing of shape can in some sense be expressed in terms of monotone double Hurwitz numbers with smaller input data. So this is essentially what the proof, how this proof works, at least in this very last paper. And we also used a representation theoretic approach in an earlier work. But this is how this tropical geometry interpretation works. And this indeed yields recursive wall-crossing structures. Okay, so how much time do I have left? I think I have like 7 minutes or something.
Actually, I would say 9 in principle because you started 3 past. So
okay,
yeah,
then, okay,
I think
could be
yeah, you have time.
Okay, great, thanks. Okay, so then I would like to, also what I wanted to say is that our results also hold for something which is called strictly monotone Hurwitz numbers, where we don't force that SI is smaller or equal to SI plus 1, but indeed SI is strictly smaller than SI plus 1, so that's why they're called strictly monotone Hurwitz numbers. And these invariants are equivalent to an enumeration of Grothendieck Saint-Dauphin. And the statements hold in a very similar fashion. Okay, so now I want to come to the last section, which is an excursion to mirror symmetry, just to mention like how this connection between Hurwitz numbers and mirror symmetry works. Okay, so the key here is that one doesn't look at double Hurwitz numbers, but one looks at something which is called an elliptic Hurwitz number. And elliptic Hurwitz numbers are deeply intertwined with the mirror symmetry conjecture. And I quickly want to define what elliptic Hurwitz numbers are. So the definition works as follows. So we fix a torus T, and we fix a positive integer D, a non-negative integer R, and we fix R points on the torus. And then the elliptic Hurwitz number NDR enumerates holomorphic maps from S to the torus, where S is a compact Riemann sphere, is a compact Riemann surface. So where S is a compact Riemann surface, Pi is simply ramified. In other words, the ramification profile is 2 and then only once, and all the other points on the torus are unramified. So once again, this is a Riemann surface. There are non-constant holomorphic maps from the Riemann sphere to the torus. I'm very sorry. So in the double Hurwitz numbers case, what we looked at, we enumerated non-constant holomorphic maps from a Riemann surface to the Riemann sphere. And in this case, we enumerate non-constant holomorphic maps from a Riemann surface to a genus 1 Riemann surface. So we move from the genus 0 case in the target to the genus 1 case in the target. So in 1995, Dijkgraaf confirmed 2 predictions of the mirror symmetry conjecture regarding the structure of elliptic Hurwitz numbers, and one of these predictions is the following. So Dijkgraaf proved in 1995 that if you take E2, E4, and E6 to be the Erhard series, which are given as this, the important thing to know is that this is a generating series in a variable Q. Then we have that for any fixed R bigger or equal than 2, so we have to fix R bigger or equal than 2, then we have that the generating series of elliptic Hurwitz numbers is a rational polynomial in these Erhard series. And this is what is called a quasi-modular form. So this is one of the predictions of mirror symmetry, and digraph proved that this is indeed true for elliptic Hurwitz numbers in 1995. So one of the interesting things about these quasi-modular forms is the following. So Eskin and Konkov proved in 1999 that this quasi-modularity property allows to study the asymptotics of elliptic Hurwitz numbers as d approaches infinity. So in general, the asymptotics of Hurwitz numbers, so the study of asymptotics of Hurwitz numbers is a very difficult problem, and most of the questions are still open. But in the case of these elliptic Hurwitz numbers, this quasi-modularity property allows us actually derive what the asymptotics of elliptic Hurwitz numbers are. Okay, so we asked the question whether this also holds in the monotone Hurwitz numbers world. So elliptic Hurwitz numbers, first of all, may be also expressed as factorizations in the symmetric group. So elliptic Hurwitz numbers equivalently enumerate factorizations tau 1 to tau r, alpha beta, where the tau I are transpositions, and alpha beta are any permutations. And we also have that the product of tau r to tau 1 is equal to alpha beta minus 1 beta minus 1. So this is the higher genus analog of Hurwitz's theorem. And of course, because we have r many transpositions here, we can also impose a monotonicity condition on the bigger element of these transpositions, and therefore analogously to double Hurwitz numbers, this gives rise to a notion of monotone elliptic Hurwitz numbers NDR. All right, great. And so then in a joint work with Jan Willem van Itersum and Felix Leit in 2019, first of all, we showed that elliptic monotone Hurwitz numbers also admit a tropical interpretation. So this is what we proved in 2019. And using this tropical interpretation, we see that the generating series of monotone of elliptic monotone Hurwitz numbers is also a quasi-modular form. So in other words, it's a polynomial in these Erhard series E2, E4, and E6. Once we fix r bigger or equal than 2. And once again, this also holds for the strictly monotone Hurwitz numbers case. Yeah, and that's it. That's the end. That is the end of my talk. Thanks a lot for your attention. I look forward to questions.